significantly reduce the tail latencies. So the impact of latency on user experience has been widely studied over the past decades. Companies like Google and Amazon have shared their experience with customer satisfaction and performance variations in their products. So Amazon found that every 100 milliseconds of latency cost them 1% in sales, and Google found that an extra zero point 0.5 seconds in the search page generation time dropped their traffic by 20%. So latency is tightly coupled to the user experience. So to reduce the observed latency, different solutions have been proposed at various levels of the network communication. So various features like asynchronous loading of web page elements, request pipelining, and request multiplexing has been introduced in the web page design to cut the page load time. Similarly, concepts like content delivery networks are widely adopted to reduce the request serving time for the clients based on its location. To avoid bottlenecks at the routers and for better availability, multipath routing was also introduced. Load balancers exist at the entry point of a server farm to choose the leastly loaded server so that the client request incur a lesser waiting time at the server. So once the request reaches the server machine, techniques like DPDK and eBPF helps to speed up the processing time of the request by the application. So many of these solutions in turn use latency as a metric to take control plane decisions. So CDN uses latency to decide the placement of CDN nodes as well as for redirecting clients to the closest server in the terms of latency. So in this example, with a new set of customers, the CDN provider will check if the latency from these new customers to the existing CDN servers is higher than an acceptable value. If it is higher than an acceptable value, the CDN provider may choose to host a new CDN server close to these customers. In the case of routers, if there is a multipath available to a destination, in this example, to reach R7 from R1, there are two paths available, one through R2, R3, and the other through R4 and R5. Based on the latency incurred on the packets forwarded over each path, router R1 can infer the bottleneck on an upstream routers. And based on the degree of the bottleneck, router can proportionately move traffic from one link to another. In this example, initially router R1 splits the traffic equally across the two links. At this point, we assume that all the routers in the paths are lightly loaded. Now, when router R3 receives packets from R6 as well, due to the difference in the incoming and the outgoing rate, router R3 may become the bottleneck. So as a result, packets may experience some queuing delay at R3. So if the router R1 can sense this delay, it can take a corrective action of diverting a fraction of traffic to router R4. So this will help in a better utilization of the network resources. Similarly, load balancers can make meta decisions on forwarding requests to the server if they know the load of the backend servers. In this example, initially all the servers, we assume it to be lightly loaded. LB forwards, the load balancer forwards the request equally to the backend servers. Suppose that now S1 becomes loaded. Now the request forwarded to the server S1 may incur a delay in its response. So if the load balancer has this delay information, it can infer the load on the server and proportionately move the new request to other backend servers. So this can also help reduce the load on the server and thereby allow better utilization of the resources on the server and also improve the performance observed by the client. So there are a number of delay measurements that are possible. So I'll go over a couple of them. So round trip time, otherwise known as RTT, is a time a packet takes to reach the destination and back. So the time it takes for a request to reach the server and get an acknowledgement back is the closest to the round trip time. Similarly, the time from the user's request to the receipt of the first byte of data is the time to the first byte, which indicates an application's response time. Next, we have the time to last byte, which is the time it takes to complete the request as well as the response. So when there is a severe resource contention on the server, the time to the first byte and time to the last byte can differ significantly. And our experiments found that RTT is not a good representation of the delay in the application processing. So we are interested in measuring time to last byte, as a client would not be able to progress with the partial data. So from these studies and observations, it is evident that the effectiveness of any latency-driven techniques in improving the application performance, it depends on the accuracy as well as the granularity of the latency measurements. So from this graph, we can see that initial connection establishment time, which is a green curve, and the RTT, which is a network delay, represented by the orange curve, they differ from the actual application delay by a significant amount. So we have to be specific of what we want to measure. Similarly, the measurement technique should also scale with the number of connections and the request. So there are many solutions that exist currently for latency measurement. The first technique is active probing. So if a measurement node or a monitor want to find a load on a particular server, what it does is it send a probe request to the server querying about its load. The server will send a response saying what its load is. So to have a granular latency measurement, the monitor or the measurement node has to send this probe request in a frequent interval. So RTT. So one of the main advantage of this active probing is that it can get accurate load information from the server directly. But the disadvantage is that it incur a network load as well as a compute load. Now, to get the granular latency or the load measurement from the server, the probe rate has to be high frequent enough. Another technique which exists is the segment measurements. So this is widely seen in the routers. So here what it does is it is trying to localize the measurements within one segment or a few segments. It doesn't calculate the end-to-end application response latency. Another kind of measurement that is there is the RTT measurements. So RTT measurements are usually done by an intermediate node by associating the sequence number of the request, which is available in the transport header, and the acknowledgement number in the response. So RTT is calculated as the difference between the time at which a request has been received and the time at which the corresponding acknowledgement or the response has been received. Google has incorporated a large-scale latency estimation system based on RTT into its content delivery network. But the main disadvantage of this technique is that it tries to figure out the network delay, but not the application response latency. So with the existence of so much solutions for latency measurement, why are we interested in doing a latency measurement study now? So with the adoption of secure transport protocols like QUIC, the transport headers becomes encrypted. So the informations like the sequence number and the acknowledgement numbers that has been widely used for RTT calculation will not be visible for a middle box. Similarly, with the design choices like deploying a load balancer in a direct server return mode, asymmetric routing becomes even more prominent. So measuring latencies with existing solutions is more prone to failure. So the requirements to measure latency have shifted to handle to being able to handle encrypted transport and the application headers. Similarly, it should handle routing asymmetry. It should be capable of generalizing it across transports and transport algorithms. And it should support an efficient deployment on the software middle boxes. So we introduce Pirate, a technique to address these new requirements for latency measurements. So the main problem that we are trying to address with Pirate is the capability to measure latency from an intermediate passive measurement node, which has no visibility into the response, either due to asymmetric routing or due to the payload or due to the transport headers being encrypted. So if we don't have the visibility into the response, how can a passive measurement node measure the latency? So in Pirate, our first idea is to leverage the closed loop nature of the internet protocols and applications. With a closed loop system, there is some kind of dependency between the requests. So these dependencies can be an application dependency. So in the case of application level dependency, a new request R2 is triggered only after the previous response has been processed at the client. The another kind of dependency is a protocol dependency. In the case of protocol level dependency, a new request is triggered once the transport protocols on the receiver has acknowledged the receipt of the previous transmissions. So here we call in the first scenario, we call R1 and R2 to be causal pairs because R2 is caused by the processing of the response for R1. Similarly, R1P1 and R1P4 are called as causal pairs because it is only after the transport level acknowledgement for the packets from R1 through RP3 that the client sends the next request, which is R1P4. So the packets triggered by the previous response can be used as a proxy to estimate the client visible request to response time. So the second idea, if we have the causal pairs to measure the latency, how can we identify these causal pairs? So the main idea is to use the time gaps between the packet arrivals to identify these causal pairs. A single request can be split into multiple packets from the client. So in this example, R1 through R3 are part of the first request, represented by batch P1. It receives a response. When the client receives the response, it sends the next set of requests, which is split across R4 and R5. And this is part of the triggered request, represented by batch P2. That is, batch B2 is causally related to batch B1. But how can the passive measurement node know which packets are causally triggered by the previous packets? So our approach is to use the idle period between the two batches, that is batch B1 and B2, to distinguish the causal pairs. So a sufficiently long pause, which is the idle time here, can be used to differentiate the causally triggered packets from the previous ones. So idle time or the prominent gap between consecutive requests can be used to detect the triggered request. But when a client sends a request to the server and the server reply with a response, the client observed latency is T client. So the main idea is that if this response triggers a subsequent request from the client, then we can get an approximate value of T client or in the passive measurement node as T pirate. It is the elapsed time between the initial request and the triggered request. But there is a small approximation error here, which is the client think time. So the client think time is the idle time between receiving the first response and submitting the second request. Now, as we have the interpacket gaps, how can we maintain it in the measurement node? To produce a response latency from these interpacket gaps, we maintain a distribution of the interpacket gaps over a period of time. This is because to produce a response latency instantaneously after each causal pair, it is subjected to determining a pause time threshold, like the interpacket gaps. If it goes beyond a threshold, that is an idle time. So in contrast, we observe that maintaining a distribution of the interpacket arrival gaps over time can provide meaningful clues. In this distribution, it has two modes, intra-batch and inter-batch. So intra-batch represents the interpacket gaps that is observed within a batch, whereas inter-batch represents the interpacket gaps or the idle time that happens between the two batches. So as the distribution has two strong modes with 50% probability, we can calculate the latency as the sum of representative values from each mode. So the representative value could be an average of all the samples within a mode. So the usual way of maintaining a distribution is to maintain a histogram with fixed size buckets or bins. However, the problem with this approach is that in measuring the network latency, we don't know upfront what the range of latency values would be over a connection lifetime. It can differ within a connection as well as across connections. So as more components are involved in processing the request, there is more variance, and this range can vary significantly. So the plot here shows a possible scenario. In the first plot, the latency range is 1.5 millisecond. In the second plot, the latency range is 2.5 millisecond. And in the third plot, it is 200 milliseconds. So identifying the right bucket size ahead of time can be challenging. Also, when you have to maintain a fixed size buckets, we can either maintain a small bucket size or we can maintain a bucket size which can, if the range is high, we have to maintain a huge bucket size. But there are some disadvantages with this choice. If the bucket size is too small, there would be too many buckets that has to be maintained, which will consume too much memory, and the computation will also go high. When the bucket size is too large, the samples from different modes may end up in a single bucket, which can significantly reduce the bucket's average contribution to the latency estimation. So to mitigate the inaccuracy resulting from the fixed size bucket scheme, we propose a new scheme with Pirate. So we start off with n buckets. So in this example, it is like 10 buckets, and each bucket its bounds will be initialized to 0. So a bucket holds what is the minimum value that it has seen, what is the maximum value of the interpacket gap that it has seen, and sum represents the sum of the samples within that bucket, and count represents the number of items that has been added to that bucket. So we try to find the candidate buckets as the samples arrive using the proximity principle. So assuming that the proximity principle is a sample S is said to be in a proximity to an existing bucket B with bounds min and max if it falls in the range min minus delta to max plus delta. So assuming delta equal to 10 for this particular example, when the first sample comes, since there are no samples collected till now, we put it into the first bucket, and update its bounds. So min is updated to 50, max is updated to 50, sum is updated to 50 and count is updated to 1. Now, the range of values that can be added into this bucket would be 50 minus delta, that is 40, to 60, which is 50 plus delta, min minus delta to max plus delta. Now, when the second sample 180 comes, since it is not in the range of 40 to 60, we add it into a new bucket and initialize its bounds and sum and count. When the third sample 60 arrives, since it is in the range of the bucket B1, it will be updated within the bucket B1 and its min will remain as 50. Its max is now updated to 60. Sum is updated to 50 plus 60 and count is updated to 2. Now, one interesting thing is that the range for the bucket B1 has now changed from 40 to 60 to 40 to 70. Now, when sample 175 arrives, it will be updated within the bucket B2 with the same proximity principle. Now, on sample 55, it is updated within the bucket B1. So, this maintenance of the online distribution is divided into two phases. So, this phase is the sample collection phase. So, the sample collection happens for over an epoch of time. Once that epoch of time completes, at that time interval completes, we had to find the latency observed during that time interval. So we move into in the first phase, which is the sample collection phase, we maintain the distribution with proximity based inclusion into dynamically sized buckets. Now, in the second phase, when an epoch of time is over, we estimate the latency. So latency is estimated as the weighted sum of the latency due to the inter-batch gaps. So here we have 3 buckets. Assume that we have collected the samples and we ended up with 3 buckets. And bucket B3 represent the inter-batch gaps. And bucket B1 and B2 represents the intra-batch gaps. So in this example, B3 holds the inter-batch gaps. So latency is calculated as a weighted sum of the latency due to B3. So since bucket B3 has 2 samples and bucket B1 has 10 samples, for one sample from B3, we take 5 samples from B1. And for one sample from B3, we take 2 samples from B2 because B2 has 4 samples. So the latency estimation would be each of the bucket contribute some value towards the latency estimation. So that is calculated as the number of samples from each bucket into its contribution. So from bucket B1, it would be 5 samples with an average of 40. From bucket B2, it would be 2 samples with an average of 165. And from bucket B3, it would be 1 sample with an average of 450. So the final latency estimate from this scheme would be the weighted sum of the contributions from each of the buckets. So we have found ways to generalize this to cases where multiple buckets of interbatch gaps exist. So in addition to the new scheme of maintaining a distribution, we also use 2 heuristics to reduce the error in our measurement. The first one is ACK coalescing. So interpacket gaps due to the acknowledgements are very noisy. So we omit the interpacket gaps due to the acknowledgements and include only the interpacket gap due to the data packets. And the interpacket gaps due to the data packets, it implicitly includes the interpacket gaps due to the acknowledgement. The second one is MTU. So a packet with length less than MTU is used as an indicator of the last packet within an batch. So any questions on the technique?
There's no questions so far.
Okay. Okay, then I'll continue with the evaluation. So we evaluate pi rate in three settings, one within a local area network with one client machine, one server machine, and a measurement node in between. The measurement node lies in the path of the client to the server. The response doesn't pass through the measurement node. And in the second setting, send a cluster. We have a cluster which spans across three regions. One is Utah, the other in Clemson, and the third in Wisconsin. The measurement node lies in the Clemson cluster. As in the first case, the measurement node doesn't have the visibility of the response traffic. And in the third setup, we want to use the latency measurements for control plane actions like load balancing. So in this case, in this setup, we have two machines, two client machines, four server machines, and a measurement node or a load which also does the load balancing. So we use the open source load balancer, Catran from Meta. So all these machines are connected via a switch. So Pirate's latency measurement is integrated into the Catran to update the weights of the servers in its maglev hash table computations. So to evaluate our technique, we answer the following questions. We want to measure how accurate our measurement technique is in estimating the application end-to-end latency under different settings. So we evaluate our technique with different applications like web workload, memcached, video playback, etc. We also evaluate our technique with protocols like QUIC. In all the evaluations, the baseline metrics that we use to compare our technique is the request to response latency, which is observed at the client. So we compare the following metrics. We compare the client-side request to request against the client-side request to response. This helps to identify how well the idea of approximating request to response with request to request hold true for an application. Then we compare the pirate measured request to response with the request to response, request to request with the request to response on the client. This is to identify the accuracy of pirate. And finally, we want to quantitatively measure the usefulness of latency on control plane actions from an intermediate node. So we show the impact of latency in the load balancing decisions. So to start off with, in our first experiment, we tested the accuracy of pirate against the request to response observed at the client for a web workload. We also compare the request to request observed at the client against the request to response observed at the client. So the graph shows that absolute error of request to request and pirate from the baseline, which is request to response. So the request to request observed at the client differs from the baseline by a few tens of microseconds. Pirate differs from the baseline by a few hundreds of microseconds. So the graph shows that the relative error of the request to request and pirate from the baseline is almost 0%. So pirate has a relative error of minus 15 to 15, but it is 0% in around 80 to 85% of the cases. Now, in this experiment, we tested the accuracy of pirate against the request to response observed at the client for a web workload in a wide area setup. We also introduced congestion by introducing a cross traffic of 0%, 20%, 40%, 60%, and 100%. The graph shows the relative error of pirate from the baseline at different levels of congestion. So this proves that the accuracy of pirate in a wide area setup is also good so it is within 15% of the request to response observed at the client for more than 90% of the time. So next we try to evaluate our technique with a different application, which is memcached. So memcached is a NoSQL key value store. We tested the accuracy of Pirate with a memcached workload, and we use memtier as a benchmarking client. So the memtier benchmark is run with a total of 10 threads with one client connection per thread. So the proportion of the get and set request is 1:1. The data size for the responses is in the range of 40 to 10,000 bytes, and the benchmark was run for 2 minutes. So the figure shows the CDF of the latency estimated by the baseline, which is the request to response at the client, and the pirate, which is measured in the intermediate node. So as you can see, the pirate closely follows the ground truth measured at the client. Now we evaluate the accuracy of pirate for video traffic running over an emulated cellular network. So to do that, we play a Dash video stream using a headless Chrome browser on a Mahi Mahi network emulator. We collect the ground truth response latencies for each downloaded video chunk using the browser's built-in Chrome developer tools. We also applied a T-Mobile LTE network trace to emulate both the uplink and downlink of a cellular network on top of our experimental wide area network topology. So the accuracy of Pirate is a bit less compared to the previous cases. So this is mainly due to the client think time. So once a response is received on the client, it have a huge amount of think time, which causes that approximation to be on a higher side. So errors in the estimation based on quasi pairs can be significant with Pirate. And in this case, it comes almost entirely from the client think time. So that can be seen from the figure on the right. So it closely follows the Pirate's value. And if you see at the top 20% of the time, it almost matches the client think time, almost matches the Pirate's time. And that corresponds to almost 100% of error in the left figure. Now, we also wanted to test our method with secure transport protocols like QUIC. So here we tested two scenarios when the response of all the requests in flight are small enough to fit into a single packet. So that is represented by the figures which has a label of no ACK. And the second case is when the response are larger and it trigger ACKs from the client. And this is labeled which has a suffix of with ACK. So Pirate uses one of the two heuristics that we use is the ACK coalescing. So Pirate's ACK coalescing heuristics requires differentiating pure acknowledgement packets from those that contain data. So this feature is not readily available by inspecting the QUIC protocol headers. So our measurements for the scenario 1, where the response doesn't trigger acknowledgement from the QUIC, the accuracy is exact. In the second case, we simulated the correct identification of the pure ACKs. The result affirms the potential utility of Pirate to measure multiplexed encrypted transports. So in the future, we believe that either an extension to the protocol or heuristics based on the payload sizes may be applied to accurately identify pure ACKs within QUIC and practically realize these benefits. So in the next experiment, what we are doing is we are using the latency that we measured with Pirate, and it is integrated into the Catran load balancer. So we compare the 99th percentile tail latency of this Pirate enhanced latency aware Catran and the unmodified Catran. The latency aware Catran is able to reduce the tail latency And also the tail latencies are predictable, as you can see from the error bar. The error bars are shorter in the orange curve compared to the green curves. So the pirate enables reducing the 99th percentile tail latency by 37% on average across the different loads. So to conclude, pirate can approximate the request to response latency observed at the client with high accuracy. Pirate is accurate across deployments like local area network, wide area network, and cellular networks. Pirate works reasonably well with secure transport protocols like QUIC. Pirate works across different applications like web workload, memcached, and video streaming. And Pirate can also enable better control plane actions like load balancing. So thank you for listening, and I'm happy to take questions.
All right, thank you very much for going through that. So I've given everybody the ability to unmute yourselves if you want to ask a question, or you can always type it into the chat room or raise your hand. So I had one question just to sort of get us started here. Um, in our talks here, we spend a lot of time working on things like bulk data movement and things like that. Have you tried to use this for anything besides those different applications so far? Maybe trying to use this with a tool like Globus or Grid FTP or anything that's moving large amounts of data?
Which is the application that you have mentioned? Could you please repeat?
I'm sorry, like Globus or FTP or SFTP, and anything that's really involved in bulk data movement.
So one of the application which is the video streaming. So the web application payload, the web workload, as well as the video streaming, it spans to a few MBs of data, but not in terabytes or anything. But the max we have gone would be a few gigabytes of data with the video streaming and web workload.
Okay, thank you. Does anybody else have any questions that they'd like to ask? Okay, so Scott from NCAR says in the chat room, has this been deployed in a production network? What would be involved in using this in a production network? What tool could present the results?
So we have the closest to the production network that we have used is like using this latency measurements to control to make load balancing decisions with CATRAN. So, and that too, using it for load balancing with CATRAN, we have tested it with our local setup. It is not something which we have deployed in a production network like Facebook or Google or anything. But we have simulated the workload, which is by collecting the distribution of the data packets, data size from the Google trace. So using that, we have simulated some kind of uh, production environment.
Okay, thank you. Does anybody else have any other questions that they'd like to ask? David put in the chat room, how does this perform in a heavily loaded network? If the host is working hard, it might slow the acknowledgement.
Yeah, so the main thing is like even the middle box doesn't see the response. So if the server is loaded and it is not able to respond, it is visible on the client as a higher response latencies. So we will be able to, so the client, when it observes higher response latencies and it doesn't get a response, it will further slow down the further request and the triggered request. So that will be captured by the intermediate node, measurement node. Does that answer the question?
Well, David hasn't responded, but I'll assume that it did. Does anybody else have any questions that they'd like to ask? Great. Well, thank you very much for going through. And if you can send me a copy of the slides, we'll post these along with the video into the usual location. And
Okay.
for others that are on the call, our next call isn't going to occur until October 10th, and that will be with Brenna Mead, Tom Costello, and Jan Zahn, and they will be going over some information on IPv6 transition on Cynet's SC24 network. So thanks everybody for joining, and we'll talk to everybody in a couple weeks.
Thank you.